Welcome to CSI Training. Here at CSI, we are seriously committed to helping you achieve your goals in your reliability-based maintenance programs using predictive and other proactive maintenance methods. Whether you've just been assigned to the vibration monitoring team or been a valuable player for many years, we're sure you will benefit from the tips and concepts presented in this program entitled Data Collection Techniques to enhance your abilities to obtain the most valuable data for trending and diagnosing machinery conditions. Some questions often asked are, why do we need to collect data so often? And why can't we just collect data when there appears to be a problem? These are the first questions we will answer. Other questions include, which is the best sensor to use? And where are the best data points on pumps, motors, gearboxes, belt-driven equipment, and pillow block bearings? All of these questions and more will be answered. The previous program, Introduction to Vibration Analysis, showed how the spectral and waveform data we acquire is a representation of energy actually occurring within the machine. This program builds on the previous program and shows how to get the best data that is an accurate representation of the energy actually occurring in the machine. By applying the information presented in this program, you will be able to acquire the best possible data that will aid in the machinery analysis. Although vibration monitoring has been done in various ways for many decades, it is only in the last few years that routine vibration monitoring has been widely used. With the advent of portable data collectors and PCs, came the ability to acquire and store spectral and waveform data. Vibration monitoring programs have proven effective in reducing overall costs for industrial plants. Since vibration monitoring can indicate the health of a machine, these predictive maintenance programs, or PDM programs, can prevent machinery damage and costly delays caused by unforeseen machinery failure. There are two concepts for monitoring equipment like this. The first is, only collect data when a problem is suspected, and at that time do an in-depth immediate analysis. The second concept is, monitor the machine on a periodic basis and trend the data for any change that would indicate a developing problem. Analyzing a machine only after a problem has been detected seems to be a logical labor-saving concept. The drawback to this is, we may never know there is a problem until a failure is imminent or has already occurred. The damage caused is often much more severe and costly to repair than problems corrected at an earlier stage. However, when a machine is routinely monitored on a periodic basis, variances in the data indicate changes in the machine. These changes can be analyzed, and the problem can be determined, allowing ample time for ordering parts and scheduling a downtime. In summary, routine periodic data collection and analysis yields increased uptime, decreased maintenance and repair costs, increased lead time, as well as a trend useful for determining machinery life expectancy. To maximize the benefit of collecting this data, especially trending, certain conditions must be met. The data must be collected at the same locations, in the same way, using the same sensor type and the same sensor mounting. The general rule of thumb is, acquire 2 radial readings per bearing location and at least 1 axial per shaft. The radial reading should typically be the horizontal direction and the vertical direction. These radial readings will give the analyst an idea of how the machine is moving up and down as well as side to side. For horizontal machinery such as this, where the mounting is at the bottom, we typically would expect less movement up and down because it is limited by the mounting. The analyst compares these vertical readings to the horizontal readings to check for problems, such as a soft foot condition or loose mounts. An axial reading is one which is the same direction as the shaft or axis. In this motor, the axial measurement could be made at either end. We use the axial measurement to indicate how much the shaft is moving from end to end. Theoretically, the readings at one end should be the same as the other, since the same shaft extends the length of the motor. Actually, the readings will vary some from end to end, due to possible differences in mounting positions and the physical design of the machine. So in order to get the most useful data for trending and routine analysis for each machinery component, collect a horizontal and vertical reading at each bearing location and at least one axial reading per shaft. Some suggestions should be made regarding the location of collection data points. A previous section identified the need for horizontal and vertical measurement at each bearing location, as well as at least one axial measurement per shaft. The magnet with two poles can be used on a wide variety of surfaces. If the machine has a smooth area, such as this one has, the magnet mount can be placed directly on it. The outboard end of this motor poses a special problem. The only smooth area is on this fan cover. Using its surface for mounting does not give an accurate picture of the motor vibration, but simply the energy of the cover, which may be transmitting only a very small portion of the actual machine vibration through it. With the cover removed, we can get a better idea of what we are trying to achieve. This is the fan, and the bearing we need to monitor is further inboard, here. The best reading could be achieved by removing the fan cover and placing the sensor on the casting near the bearing. Obviously, this is not an option, since the cover must be in place while the data is acquired. The alternative is to collect data through this area of the motor. With these cooling fins spaced closely together, it becomes necessary to place the magnet mount on the fins. It could be placed across the fins or in line with them if the magnet's two poles will line up. For routine data collection, remember that we may not be able to take the time to get the best location, but that the data should be repeatable. This makes trending a valuable asset to the analyst. Although the horizontal measurement could be made on either side and provide good information, it is best to maintain the same horizontal measurement orientation from one routine survey to the next. The analysis equipment is so precise that even minute differences from one side to the other can significantly alter the data. The best place for an axial measurement is near the shaft center and on the bearing in the load zone. The load zone is the radial direction the most force is applied during normal operation. In horizontal machines, this is usually in a clock face position of 4 to 5 o'clock or 7 to 8 o'clock, depending on the direction of rotation. The axial measurement on this motor could be made at any of several places. The simplest place is on the end bell at the recommended clock face position, but the same restrictions apply for this axial measurement as for the radial measurements. Don't make measurements on the end bell, as it will only be an accurate indication of the bell's movement, not the machine's movement. If no better place is available, the axial reading could be made on a through bolt that fastens the end bell to a solid part of the motor. Be sure the bolt is tight. Long bolts may have resonant frequencies that substantially reduce the linear response range of the sensor. Another usable location is the lift hook. If the lift hook is simply a loop, be sure to make the measurement at the base of the hook. If the lift hook is an integral part of the housing and of substantial size, it could be used and still obtain reliable data. Be sure the sensor is pointed in the true axial direction. The motor foot provides another location for the axial reading. If it is used for the axial measurement, the analyst needs to keep this in mind when analyzing the data. Because the foot is firmly fastened, any axial movement will be minimal. An axial reading on the lift hook would have more freedom to move and thus would have much higher levels of energy. When comparing amplitudes for radial versus axial readings, keep this in mind. Never use the electrical junction box for an axial measurement, even when it is a heavy casting of the motor housing. Data taken here will have higher levels of electrically related frequencies that may indicate motor problems that don't really exist. On the pump, the horizontal measurements should be made on this flange because the bearing is mounted directly in line here. Be sure the sensor does not cross the joint, which may cause it to rock and generate erroneous frequencies. The center section of these pumps is hollow, and measurements should not be made here, as the signals will not be accurate. The outboard bearing is located in this area, and the horizontal readings should be made here. Axial measurements could be made at either end of the pump, but the impeller end tends to show energy due to flow, which can mask other problems. The same criteria apply to vertical mounted pumps and motors. 2 radial readings at each bearing location and at least 1 axial reading per shaft. The radial readings should still be 90 degrees apart, but should be called X and Y direction. Machines that use pillow block bearings require another measurement to accurately diagnose certain problems. There should still be 2 radial measurements per bearing, but an additional axial measurement should be made on each bearing. Since the pillow blocks are independently mounted, it is common for them to be cocked on the shaft. The axial measurement is a good indicator of this problem, as well as early bearing wear due to heavy axial thrust. Pillow block bearings on shafts like this may be inaccessible due to guards, covers, or simply be out of safe reach. If the guard is mesh, the long stinger may be used to reach through it for the radial measurements. Although the stinger or long probe does not provide the best data, it is still far better than no data. However, it is important to collect an axial measurement on each pillow block bearing, and the guards or covers often prevent that. A better way to measure the covered pillow block bearings is to install a hatch door so that a magnet mount sensor can be used. The linear frequency range will be increased substantially to be sure to catch bearing degradation. Oftentimes, the pillow block bearing has rounded surfaces that cause the magnet-mounted sensors to rock. In cases like this, it is better to install a mounting pad for the sensor. The best way to measure guarded pillow block bearings is to install permanent sensors at the measurement locations. These sensors are then wired into a panel that has terminals for B and C cable connections. The measurements can be made without compromising safety or data quality. Remember that in most instances, the analyzer will be providing power to these sensors and that the sensor receives an electrical shock and requires a 3 to 5 second settling time. Belt-driven equipment has special considerations for selecting the measurement locations. Although the common rule of 2 radial readings and 1 axial per shaft still applies, it is the orientation of the radial readings that varies depending on machine design. When the center lines of the motor and driven equipment are in the same horizontal plane, there is no change in the measurement locations. When the shaft center lines are not in the same horizontal plane, 1 radial measurement should be made in line with the centers of both shafts, and the other should be 90 degrees to it. This inline measurement is also the direction of belt tension and is used to indicate eccentricity or excessive runout in the sheave as well as a bent shaft. The perpendicular or 90-degree measurement better determines sheave misalignment and belt resonance. It is important to acquire good axial measurements to confirm misaligned or bent sheaves. The same recommendations should be followed for these axial measurements as axial measurements on any other machine. Although the next video program in this series discusses gearboxes in depth, here we will cover the best measurement locations for them. Gearboxes have high-frequency occurrences that require exceptional data collection for proper analysis. Routine surveys for single reduction parallel shaft gearboxes require a minimum of 1 radial and 1 axial measurement at each bearing location. Use 2 radial measurements when troubleshooting problems in a gearbox. The extremely high frequencies associated with gearboxes may necessitate 2 measurements being made for each sensor location. 1 measurement would be low frequency, high resolution for detection of balance, looseness, misalignment, and bearing problems. The other reading would be very high frequency to 3 or more times the gear mesh frequency with high resolution for determining gear condition. The direction of radial measurements should be in the line of force of the gears, through the center line of the shafts. As in other measurements, we need to be as close as possible to the source of the energy with a solid transmission path through a web or internal frame to the measurement location, and as close as possible to the bearings actually supporting the gears. For multiple reduction and angle gearboxes, 2 radial measurements should be made at each bearing location as well as the axial measurement. This second radial measurement should be perpendicular to the first measurement. In order to get the best data, we need to understand some facts and limitations of the various sensors. Each of these sensors or transducers has distinctive characteristics that may make it more desirable than another for a specific application. All of these transducers are either piezoelectric velocity transducers or accelerometers. Their size, sensitivity, and linear frequency range are the primary differences. Here, we will focus on accelerometers. Inside these accelerometers is a piezoelectric crystal. This means the crystal is under pressure, and when an electric current is applied, the output voltage changes with a change in pressure. The change in pressure is produced by the vibration of a machine impacting the sensor. The analyzer reads this voltage output and stores it as your data. Because of the orientation of the piezoelectric crystal in the sensor, it is very directional. Typically, 95% of all the energy the sensor picks up is directly in line with the sensor. Only 5% of the vibration data is from a lateral direction. Because the transducer's sensitivity is very directional, it is important to get the data that will be of most benefit. In this machine, as well as most machines, we are interested in the energy generated by the rotating shaft. The rotating shaft transmits the energy due to misalignment, unbalance, bearing failures, and other faults to the casing. The sensor should be pointed directly to the center line of the shaft in order to pick up the most information from rotational energy. In order for the energy to get from the shaft to the sensor, there must be a good solid path to the sensor. The cover on the inboard end of this motor has reinforcing vanes molded into the casting. These will transmit energy from the bearing location to the sensor with little loss. However, the places without the reinforcing vanes are voids, and the energy is not transmitted as well to these locations. If you know the internal structure of the machine, collect the data where there will be a good solid path to the transducer. We need to use the characteristics of the sensor to maximize our results. Other limitations are built into the transducers that affect our data. One of these limitations is the linear frequency response range. Sensors are designed to function well in certain frequency ranges. This spectrum from a sensor mounted on a shaker table shows its linear or stable frequency range to be from approximately 2 Hz to 10,000 Hz. Frequencies below 2 Hz or above 10,000 Hz would not be accurate in amplitude. Another sensor must be used that is linear in those ranges for amplitude accuracy. Although a sensor is designed to perform well within its stated frequency ranges, there are resonant frequencies unique to the method of mounting the sensor that greatly affects its linear response range. A resonant frequency is a frequency that an object likes to vibrate at. Every object has at least one resonant frequency. When this tuning fork is struck, it will vibrate at a frequency that is dictated by its design. 3 design factors affect